Find the mass of the solid where z goes between 0 and 2, and x squared plus y squared is less than or equal to 3 plus z squared. And density function, because if you want mass, you need to know what the density is, at any given point is for z. Makes a side notation saying, what does this look like? You have your x squared plus y squared equals 3 plus z squared is a hyperboloid of one sheet. So in other words, a hyperboloid of one sheet, for those who are trying to remember, this is sometimes called an hourglass type shape. So it looks something roughly speaking like that. And so what's going on? Well, essentially we're just cutting it, and we're only taking the parts between z equals 0 and z equals 2. So it has this kind of shape to it. So that's our basic shape, and of course there's the question. All right, so how do we go about doing this? Well, we'll get to that in a second. What are our options? 10 pi, 20 pi, 30 pi, 40 pi, or 50 pi? Do we have an answer? Did somebody work this out? Somebody suggested it's at least one of them. Well, hopefully, unless there's a mistake or typos. Typos do happen. Well, before I show you the answer, let's at least reason a couple of things. What would we want to do? Like, okay, sure, we're finding mass. How do you find mass? What's that? Integral of density. Okay, so we know we have to integrate the density function. We know it's a triple integral because it's a solid. It's a three-dimensional object, so it's a triple integral. What else do we know we should be doing? Well, polar is two-dimensional. We need something three-dimensional. So we need cylindrical coordinates. Okay. All right, so we know this problem will involve cylindrical coordinates. When it comes to cylindrical coordinates, what's dv? R dz dr d theta. Now, there's some clues, of course, that we should switch to cylindrical. Do you spot any clues that cylindrical is a good choice? Certainly x squared plus y squared. If you see x squared plus y squared showing up, that's a good clue. Also, if you have anything with rotational symmetry. So my picture's not a very good picture, but you can imagine I was a better artist. If you spin it around the z-axis, you get the same shape. Now, if we are going to set this up for cylindrical coordinates, you should look in the RZ plane. And if you look in the RZ plane, you've got the line z equals 2. And then you have this curve coming into here. So this is our shape. Now, given that, there's sort of an aha thing. Is there any revision you'd like to do to that? Sorry, what?
dr.
Yeah, you don't have to go dz dr d theta. You can go in any order. Why would dr dz d theta make more sense? Well, if you do dz dr d theta, you have to go up and down. What's the issue? There's a change in behavior where you have one type of behavior, then another type of behavior. Changes in behavior means more work. And how do we feel about more work? Yeah, we're opposed to it. We don't like it. Well, on the other hand, if we slice in this direction, then there's no change in terms of what's left and what's right. And so our great aha in solving this is to recognize, oh, we can change. Okay, so what's the answer? I stalled for a minute just in case people were working on it. Any guesses? D is a great guess. 40 pi. So we've already talked through most of it. It's just a matter of saying, aha, we should switch our order. And no big surprises. 4z, that's our density. R from our coordinate system. And then we have our bounds. And nothing suspicious. It's just a matter of patiently working it through. And out comes the answer. All right. Good. Good. Well, I hope you get comfortable doing these types of problems because they're going to ask you. And I say they, but of course I'm one of them. One of us. One of us. Well, we'll ask you this on the next exam. All right, so what's the thought for today? Famous quote. A ship in harbor is safe, but that is not what ships are built for. And this is sort of the well-known, yeah, it's nice being comfortable, but you got to set out and try stuff. You got to be bold. And, you know, it's easy doing problems that are simple, that you're really comfortable with, but you got to push yourself. And only when you really push yourself are you able to achieve great things. You won't achieve great things by doing things that you already know how to do. And so be bold. Try big things. All right. So before we get to today's topic, we should practice some more. And we'll have some time on the next lecture as well to do more practice, but practice more with cylindrical and spherical. Okay, so here's a problem. Rewrite the integral negative root 3 to positive root 3, negative root 3 minus y squared to positive root 3 minus y squared, 1 to the square root of 4 minus x squared minus y squared of x squared plus y squared dz dx dy into an integral in cylindrical coordinates and an integral in spherical coordinates. Okay, so we're going to do this twice. This is a problem so nice, we'll get to do it twice. Okay, so how do we go about starting such a problem? What do we need to do? Okay, so we need to get a drawing. I like that. And in particular, we need to understand, what is this thing? All right. So let's work on our bounds. So here we have our bounds. And so we'll work on the outside bounds. What does the outside bounds tell us? It tells us about y. Negative root 3 less than or equal to y less than or equal to positive root 3. Okay. Then we go to the next layer. What's that telling us about? Telling us about x and how x behaves. Negative root 3 minus y squared less than or equal to x less than or equal to positive root 3 minus y squared. Now, before we go to our third bounds, let's start with this. Let's understand what's happening here in terms of x and y. And in particular, we say, well, if we look at the curves, x equals minus square root of 3 minus y squared, or x equals positive square root of 3 minus y squared, what do we see? What are these curves? They're parts of circles. Now, square roots, we don't like those, so we square. That's x squared equals 3 minus y squared, or x squared equals 3 minus y squared. Oh, it's actually they're the same circle. We're just seeing different sides. Okay, so what circle do we have? Well, you get the circle x squared plus y squared equals 3. So in the xy plane, it's a circle. Do we know what the radius of this circle is? Root 3, good, good. And if you look, you see that y is going from positive root 3 to minus root 3, so it's the whole circle. And the inner bounds are from the left side to the right side. Okay, so in the xy plane, there we go. There's our region. Okay, now we've got to add in our z, our z. So, what do we know about z? Well, it's between 1 and square root of 4 minus x squared minus y squared. Okay, so these are surfaces. Do we know what z equals 1 looks like? It's a plane. It's a lot like the xy plane, but what's happened to it? Moved up. Okay, so it's a plane moved up. What about this other part? Z equals the square root of 4 minus x squared minus y squared. Not quite upside down bowl. Good guess. So here, if there wasn't a square root, it would be an upside down bowl. But with the square root, get rid of the square root by squaring. Z squared equals 4 minus x squared minus y squared, or x squared plus y squared plus z squared equals 4. Okay, so let's see if we can't figure out what's going on. We have downstairs in the xy plane, I'm just going to mark, we've got our circle of radius 2. It's not part of our solid, but our region lies above this part. Then we have our sphere, which has radius 2. Okay, and I'll lightly mark some of it. But we don't want the whole thing. We want to have just the part that's above z equals 1. So what happens is there's this plane, z equals 1, and now we're like, okay, so we are this part. So we're above there. And if we've done our job right, yes, okay, yes. It's going to be exactly on top. All right. So it's a piece of the sphere. Just a part of the sphere that's been cut off. Okay, so there's our region. Any questions about our region? Okay. So, top part of sphere. Well, let's start with cylindrical coordinates. Might as well do that. And we've got to get our bounds. So if we're working in cylindrical coordinates, it makes sense to look at this in the RZ plane. What are we going to see? Well, the plane z equals 1 is just a line. Then we have the sphere. It's going to look like a piece of a circle. And it turns out that we're going over to root 3. So this is what we look like if we look in a slice. Okay. So for cylindrical, we have integral, 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 x squared plus y squared. What will that become in cylindrical coordinates? R squared. Good. dz dx dy. What will that become? R dz dr d theta. Now we can change our minds and switch the order later on, but for now, let's start there. Can we say anything about theta? 0 to 2 pi. Why do we know it's 0 to 2 pi? Yeah, you have that full symmetry. When you go all the way around, you can spin, and it's always the same. That means you've got the full revolution, 0 to 2 pi. What about r? Where does r go from? 0 to root 3. Now, there was a suggestion, negative root 3 to root 3, which kind of, in some sense, you might, well, why do we do 0 to root 3? Well, because when we do the RZ plane, we only need to do the positive part because remember, theta spins around and captures the other side. So you don't have to do negative 3 to root 3. You only have to do 0 to root 3, and remember, the spinning captures the other half. Okay, so that wasn't so bad. What about z? So we're at a particular value for r. So what's going to happen is we're going to come up and say, where are we going between? What curves? Well, what's this lower curve? 1. This is z equals 1. What's this upper curve? Well, becomes r squared plus z squared equals 4. That's the sphere. Solve for z. Z squared is 4 minus r squared. So z is the square root of 4 minus r squared. Okay, now what do you do for this integral? Yeah, we're done. We've set it up. It said rewrite it. We don't have to solve it. So cool. But we have a lot of space left. That's okay, because we still have problem left. We've got that part. Spherical coordinates. Okay. Well, let's start writing it down. Integral, integral, integral. X squared plus y squared. What will that become? Okay, great. R squared is not a bad answer. I like r squared. So we remind ourselves of a couple facts. R equals rho something. Z equals rho something. Let's see if you can remember this. Rho squared equals x squared plus y squared plus z squared. Do you remember what goes in? Z equals rho? Yes, good. R equals sine phi. Rho sine phi. Okay, so if it's r squared, we say, oh, I know how to do an r. So you get rho sine phi squared. Okay, that's just the x squared plus y squared. What will dz dx dy become? Rho sine of phi d rho d phi d theta. Right? Think of the song. It'll carry you through. Okay. So what's left? The bounds. Now, the good news about theta is it does the same thing. So where will theta go from? 0 to 2 pi. Awesome. The bad news is we got to work for the rest of this, but that's okay. A little bit of work won't hurt us. Now, we'll think about phi. You can still work in the RZ plane. So remember, straight up would correspond with phi equals 0. And so we're coming off. It's like we see it, we see it, we see it, we see it, we see it until we hit this angle. And after that angle, we don't see the shape anymore. We completely miss it. So the question is, where do we start with phi? We start at 0, straight up. We stop at that angle. Now we say, well, what do we see? Well, we see a side 1. This has side root 3. Do we know a triangle with those angles, or rather those side lengths, if you will? So the hypotenuse is 2, if that helps. Is there an angle that works? Yeah, so this angle would be pi over 3, sorry, pi over 6. You have to come from the axis there. That is a 60-degree angle. So that's pi over 3. So you have to be careful here. Right, this angle, I'll mark it, this angle inside the triangle is pi over 6. But we're not measuring phi from the axis here. We're measuring phi from the z-axis. And so that's this angle, pi over 3. Okay, and now my picture's getting a little bit too crowded, so I'm going to go again. We're still on our RZ plane. We still have our piece of our circle up here. And now we're thinking about rho. So as we head out in the direction, we say, given a direction, where do we start? Where do we stop? Okay, so where do we hit initially? Z equals 1. Now, we can't put that there, because that's not a z equals, that's a rho equals. So we have to say, okay, how can I rewrite z equals 1 in terms of rho? Yeah, so rho cosine phi is z. So rho cosine phi equals 1. So what is rho? 1 over cosine, also known as secant. So secant phi. Where do we stop? We stop at the sphere. What is the sphere in terms of rho, phi, and theta? Rho equals 2, because it's a sphere of radius 2. Rho equals a value is a sphere of radius that value. So you remember how we said x squared plus y squared plus z squared equals rho squared? So x squared plus y squared plus z squared equals 4 becomes rho squared equals 4. So it goes to rho equals 2. And now what? Yeah, now we're done. So if we want to compute this little piece here, we could do either integral, and we'd get the same answer. That being said, which one would we probably want to do? Probably the cylindrical one. So not every integral is an easy integral, but all right. So there's our practice. If we have time at the end, which we will not, we'll do more. So, but we'll have more chances. Any questions? All right. So what's the goal for today? Well, we want to talk about changing coordinate systems, which is kind of what we've been doing. But changing coordinate systems, it's really about changing variables. It's multidimensional substitution. So what do? Well, we recall some things. Every integral has 3 parts. So for changing coordinate systems, we have to be able to update each part. Now, the function, usually that's pretty straightforward. And we wouldn't be doing any kind of changing coordinate systems if it was hard to change the function. So the function, we just figured out how to rewrite that using our new variables. No surprises. For the region, we have to say, okay, how do we change that? Well, what we do is we say, well, what's bounding our region? What curves or what surfaces, depending upon what dimension we're in, bound our region? And say, how do we rewrite that in our new variables? So, for instance, last thing we did, we said, well, we have z equals 1. How do we rewrite that in terms of rho, phi, and theta? So that's the kind of thing you have to do when you're working with the region. And then there's the last thing, which is where we break our region up into little pieces. Because the idea of calculus is to say, let's take this big thing, break it into lots of little things, then add them up. But because we change our coordinate system, how we break things up can affect the size of a little piece. And we've seen this. So, for instance, when we went from Cartesian to polar, we had this factor of r. In three dimensions, when we went from Cartesian to cylindrical, again, we had a factor of r. When we went from Cartesian to spherical, we had our rho sine of phi. And if you think backwards, back to the good old days of Calc 1. Oh, we were so innocent back then. We learned about substitution. It turns out substitution is essentially what's going on here. When we talk about changing our coordinate systems, it's about just changing our variables. We're substituting one coordinate system for another coordinate system. So we say, well, suppose we have x equals g of u, and we want to do our integral from a to b of f of x dx. Well, I got to update my function. That's easy. I just replace x by g of u. I got to update the region. Well, that's not bad. You update the bounds. And then what about the breaking up into little pieces? That's what the g prime of u is capturing here. So, okay, where are these terms coming from? How do you find what's in the box? What's in the box? What's in the box? Okay, that's the question. And that's what we're after. All right, so we're going to sort of work through it a little bit here. And here's sort of the idea. And I will say computers are much, much better at drawing these things than I am. So imagine I was good at drawing, or just look at the handout. So we have a region in one set of variables, u and v, and that corresponds to a region in another set of variables, x and y. Now you might say, well, wait, hold on. I thought that the description doesn't change the shape. It looks like you've changed the shape. Well, but here, what I mean is we haven't changed the shape. We're describing them in their coordinate systems. So if you think about how do you describe a circle in polar? Well, it's like theta goes 0 to 2 pi, r goes 0 to whatever the radius is, 4. That's your description in the r theta plane. And so it warps the description. But ultimately, it's the same shape that's going to be described by these two regions. So it's like, okay, so we're thinking about breaking up into little pieces. How does that affect everything? So we're going to take just a little tiny piece and see what happens to it. Now, why a little piece? Well, because when you look at a little tiny piece, things behave pretty reasonably well. And so what that says, if you start with, say, a parallelogram over on this side, where you have a little bit of change in u and a little bit of change in v, on the corresponding piece, it's a parallelogram-ish. It's not an exact parallelogram. But if you're small, it looks very, very much like it. And of course, what happens is we're going to keep getting smaller and smaller. So the approximation keeps getting better and better. So the question is becoming, if I know the area here, what's the corresponding area there? Well, as I said, it's parallelogram-ish. And, whoops, why did I say parabola? Typo here. We're going to approximate by parallelogram. And so we have our shape. We say, well, it's very much like a parallelogram. And now, what can we say? Well, if I want to understand the side here, what I can say is it's coming from this side here. So I can say, what's happening in this direction? Well, there's a change of x with respect to u and a change of y with respect to u. And how much have we changed? We've changed delta u. So this part will capture one side. It's, again, an approximation. So x sub u is the derivative of x with respect to u. And then the other vector will capture the other side of our parallelogram. So we have two vectors. Now, the nice thing is we can use tools to find area. And if you think back, like, well, when did we find area? Cross product. And you might say, well, wrong dimension, Steve. You need 3 dimensions. That's only 2. Add a 0 on the end. So take the cross product, and when you do that, you say, okay, you get a determinant of a 2 by 2 matrix, and what you're really getting is these partial derivatives showing up. These delta u's and delta b's pull out of this determinant. So there's a sort of a moral here, which are determinants are measurements. So a 2 by 2 determinant is a measurement of an area. And particularly, it's measuring a particular parallelogram. And so this is the object we're interested in. It's called the Jacobian, named after Jacobi. So what is it doing? So it's saying how much, as you move from one coordinate system to another, how much expansion or contraction are you experiencing? So it lets you get a sense of scale. And if you look here, what do we have? Delta y delta x is roughly, it's this Jacobian delta u delta v. So in the limit, this says, hey, I can say dy dx becomes this Jacobian du dv. So that's the idea. So this part, the Jacobian, that's what we were after. Now, a couple of things. Always take the absolute value. And because you're always taking the absolute value, it turns out the Jacobian is very, very forgiving. It forgives a multitude of sins. Which is to say, if you forget which order things go in, you'll be fine. So if you say, oh, I put y sub b, and x sub b, I switch the columns. The Jacobian says, you are forgiven. I will give you the same thing. If you say, oh, I accidentally said xu xv, yu yv, and the Jacobian will say, I forgive you. I will give you the same answer. So it's pretty hard to mess up. So the moral is, just get the partial derivatives in there, and life will be fine. All right. So there are 2 Jacobians I should point out. So we can talk about what happens as we move from one side to another side, and that could be, we call it the Jacobian of u and v, but we can also talk about what happens if we go the other direction. Jacobian of x and y, which we have here. And it's what you think it should be. We just change our partial derivatives around. What would happen if you multiply these 2 together? Jacobian xy times Jacobian of uv. What should you get? And why should you get it?
1, 0, 0.
So remember, there's always the good advice. If you're asked a question in a math class, the answer is usually 0, 1, or somewhere on the board. Okay, so if you multiply these together, what should you get? 1. And why should you get it? Well, essentially, if I go and do both, where have I gone back to? Where do you start? So it says, oh, if I'm expanding, as I go over here, what needs to happen if I go this way? I have to contract by the same amount to get back to the same scale. Now, as sort of a sanity check, let's try this on something we're confident we already know is true. Let's go to polar. So, in polar, we have x equals r cosine theta, y equals r sine theta. So we're going to take and find these partial derivatives. So I'm going to take the absolute value of x derivative with respect to r, x derivative with respect to theta, y derivative with respect to r, y derivative with respect to theta. And I'm going to take that determinant. Okay, so here r and theta are taking the role of u and v. What's the derivative of r cosine theta with respect to r? Cosine theta. What's the derivative of r sine theta with respect to r? Sine theta. What's the derivative of r cosine theta with respect to x? Negative r sine theta. What's the derivative of r sine theta with respect to theta? R cosine theta. Okay, take this determinant. We're going to do an absolute value here. Cosine times r cosine becomes r cosine squared. Subtract negative r sine times sine. Negative r sine squared. Well, two wrongs. Two negatives make a positive. This becomes r times cosine squared plus sine squared, also known as r. So what does this say? dy dx is the Jacobian r dr d theta. It matches. Coincidence? No. It's supposed to. Okay. So, we mentioned when it comes to changing our coordinate systems, we have to handle the function, we have to handle our region, and then we have to handle how we break things up into pieces. This was the breaking up into pieces. So, in summary, there's a procedure we must follow. So, step 1, identify the substitution. 99% of the time it's given, because we're nice people. If it's not given, and I looked ahead at the quiz next week, there was one problem where they said, we're not going to give it to you. But if it's not given, there's sort of a clue. Channel your inner Calc 1 and say, if it's not given, what do I start looking for? So when you did substitution before, what were you looking for? Well, where did substitution come from? What rule does substitution come from? Chain rule. Chain rule deals with what? Functions in functions. So if it's not given, look for inside functions. That's usually a clue. The other clue to look for is look for weird boundary. Or just boundary. So essentially the goal of any time we do a substitution is to say we're trying to make things easier. Either we're making the function easier or we're making the region easier. So they might say, here we have this integral in terms of x and y. We want you to rewrite in terms of u and v. They might say u is a function of x and y, v is a function of x and y. They might say x is a function of u and v, or y is a function of u and v. Now, the first thing you should do, because there's 3 pieces you have to handle, is what we just talked about, the Jacobian. If they give your substitutions in the form u is a function of x and y, compute this Jacobian. So u sub x, u sub y, v sub x, v sub y. And find out what this is. It's going to be functions of x and y. And then you say, okay, this times dx dy equals du dv. And they might say, why do you want to do this? Well, this is the way to minimize work. And so you can save yourself some heartache. Now, what happens? Well, this might be very simple, or it might involve terms involving x and y. If there's any x and y, grab it from the function. And then that's going to become part of your du dv. If they give it to you, x is a function of u and v, y is a function of u and v, then say, all right, dx dy is your Jacobian, which are your partial derivatives with respect to u and v, du dv. And we'll see examples of both in the next couple lectures. Okay, so there's handling how we break things up. It's our Jacobian. Now, after you've handled your Jacobian, you may have grabbed a part of your function. So whatever's left, express that in terms of u and v. So you rewrite it in terms of your new variables. The last thing are your bounds. So what do? You say, I know my region. Find your bounding curves. And say, here are my boundary curves in terms of x and y. Now, rewrite each curve in terms of u and v. And say, in the uv, I have my bounding curves. And mark what's being bounded. That gives you your new region. Now, that's the theory. Time for the practice. Any questions? This will make more sense after you do it a few times. And, you know, as they say, the first thousands are always the hardest. And then it gets a little easier. No. 4 or 5. We should get the hang of it. Any questions? Okay. Then, here we go. Find the integral from 0 to 1, integral x squared plus x to x squared plus 1 of 6x over 1 plus y minus x squared cubed dy dx by doing a change of variables where u equals y minus x squared and v equals x. Okay, so we should identify our change of variables. Good news. They gave it to us. And they will. Other than that one quiz problem. All right. Now, we have our 3 chores to do. So the game plan is essentially as follows. Jacobian, that's always the first thing I take care of. Function, and then bounds. That's the game plan. So let's start with the Jacobian. All right, so we're going to take our partial derivatives. And this is where I say it's easy to just do whatever, it'll work out. So u sub x, u sub y, v sub x, v sub y. If you switch the order, everything will work out. And don't forget to take an absolute value. Okay, so let's just take these derivatives. Derivative of u with respect to x. Negative 2x. Derivative of u with respect to y. 1. Derivative of v with respect to x. 1. Derivative of v with respect to y. What's this determinant? It'll be negative 1 when we take the determinant, but then we take the absolute value of that, so we get 1. So our Jacobian is 1. That means when it comes to substitution, this is really easy. It tells you dy dx is, well, really what it tells you is 1 times dy dx is du dv. So that this one here goes there. Since you see x is showing up, that's attached to the dy dx side. All right, so it's going to be pretty straightforward for us to handle. So it's like, in essence, we have that piece covered. Okay, what's our next part in our game plan? Function. So we have to take 6x over 1 plus y minus x squared cubed and rewrite that in terms of u and v. So usually you just say, look for chunks of u and v on the inside. So for instance, 6x, is there a way to write that in terms of u and v? 6u. 6v. 1 plus y minus x squared cubed, is there a way to rewrite that in terms of u and v? Yeah, 1 plus u cubed. Great. Now the function's done, right? We should be updating. We've taken care of the Jacobian. We've taken care of the function. The bounds, we must remember the bounds. Okay, so let's talk about our current bounds. And what do we have? Current bounds. Well, we have that x goes 0 to 1. Y, that goes x squared plus x up to x squared plus 1. So normally we'd give you a picture, so I'm just going to give you a picture here. Here's 1. X squared plus 1, I think you can probably sketch that one. What does x squared plus 1 look like? It's a parabola. What have you done to it? You moved it up 1. So here's x squared plus 1. What about x squared plus x? Well, it starts at the origin, because if you plug in x equals 0, you get y equals 0. By the time you get over to x equals 1, what do you get? You get the 2, which actually matches here. So it looks something like that. Technically, it goes down a little bit. So this is our region. It's kind of a triangle, because it is a triangle. It's just the sides are bentish. But maybe it won't stay bent after we finish our substitution. All right, so we have y equals x squared plus 1 is one side, y equals x squared plus x is one side. What's this side? X equals 0. So we have 3 bounding curves. You say, all right, let's handle our 3 bounding curves. So x equals 0, y equals x squared plus 1, y equals x squared plus x. So remember, we have u and v. X equals 0. Can we write x in terms of u and v? Okay, what does it become? V equals 0. All right. Can we rewrite y equals x squared plus 1 in terms of u and v? Well, notice we have a y and an x squared. This is the same as y minus x squared equals 1. What is this? U equals 1. What about this one? Well, let's do the same. Y minus x squared equals x. What's the bounding curve? U equals v. So we're going from our xy description, and then in our new coordinate system, we'll have u and v. Well, u equals v is a line, straight line, diagonal. U equals 1. V equals 0. It's bounding this triangle. So that's our new region. Okay, so now we have our new region. We have everything to put our integral together. Okay, so we're going to have an integral, the function 6v over 1 plus u cubed. The dy dx, du dv, or dv du. So which one do you want to pick? If you actually had to do this integral. Why dv du? Good choice, but why? Yeah, because I don't want to integrate that with respect to u. But I could integrate that with respect to v and not have a panic attack. Okay, so where does u go from? Zero to 1, because here's u equals 1. This point is at 0. Where does v go between? 0 to u. Now that's the setup. We're out of time. If we integrate once, this becomes 3u squared over 1 plus u cubed. Then you say, oh, that's a log of 1 plus u cubed. Evaluate from 0 to 1, which is log of 2. So that's not so bad once you've done the substitution. All right, that's it for today. See you next time.